Okay, now that we've got a way to sort of just get our handle on uncertainty, we'll deal with time in a little bit. Let's do something with it, okay? In particular, let's think about how do you value a gamble? Let's suppose you've got the following situation, okay? A gamble is proposed to you. If you win, you get, we'll just call it X, okay? And that happens with 50% probability. If you lose X. And that also happens with 50% probability. Otherwise, you have Y to begin with. Okay? So, how do we think about this? Well, let's begin by thinking about what's the expected value. So, expected value is what's going to happen on average if you do this a lot of times. Okay? So, let's take down here. We denote it with this capital E and then in brackets. So the expected value of this gamble, which I'm going to denote with a C, so the expected consumption that you get from taking this gamble, well, with 50% probability, you get X and Y, so you end up with X plus Y, because you always have Y to start with. That's like your baseline income, and then we add this win or loss. But with 50% probability, you lose, and then you have Y minus X. And we can multiply this out, and you get 0.5X plus 0.5Y plus 0.5Y minus 0.5X. These guys cancel out, and these guys get combined, and this is all equal to Y. This is a fair bet, okay? With 50%, you basically on average end up exactly where you started. Okay, so does that mean that we don't care about this bet? Like we're indifferent between taking the bet and just not taking the bet? Well, to do that, we have to not consider the expected value of the bet. We don't consider just the expected value of what we win. We consider the expected utility we get from winning. So that's a little different, okay? The expected utility we win looks like this. So instead of putting a C in here, I'm going to put a utility, and I'm going to actually put my utility function. And with 50% probability, we win. And if we win, we get X plus Y. But we now are we're saying we get the utility that you would get from X plus Y. Notice that there's just X plus Y together is your consumption, because it's just like money. It's how much stuff you can afford. With 50% probability, we lose. And we end up with the utility of Y minus X. And what's important is that this is not the same thing as the utility of Y. Okay? So the expected consumption is just Y. You end up back where you started. But the expected utility of taking this gamble is in general not going to be the same. Let's see why. Well, remember in the last slide, the last video, I drew this kind of diagram. We had consumption on here, and on the vertical axis we drew our utility, and we had sort of this kind of curve to it. Okay? This utility function exhibits what's called diminishing marginal utility. So I'm going to write that down. But I lost it. All right. Diminishing marginal utility. It means that as you get more consumption, so more income, for example, your satisfaction increases, but by a smaller and smaller amount. Okay, so that extra dollar means a lot to someone who's in poverty, but that extra dollar means almost nothing to Bill Gates, for example. And most people are somewhere in the middle. So if you've got this kind of utility function, we can make a kind of graphical argument about what this gamble looks like to you. So let's say Y is here in the middle. If you lose X. So let's say this is Y minus X. If you win, you get X. So we go an equal amount in the other direction. And we can essentially check out our utility function, the value that we get in those utility functions by going up and over, okay, following that utility function. So this is the utility of the bad outcome where you lose, utility of y minus x, and this is the utility of the good outcome where you win. That's utility of y plus x. The utility that you would get if you could just get that y is the thing in the middle, but you don't actually get the utility of y. That's the utility of y. We want the expected utility of winning and losing. So if you lose, you're down here with 50% probability. If you win, you're up here with 50% probability. Or we could look over at this line, and this line over here says that if you win, you're up here. If you lose, you're down here. 50% of the time you're up there, 50% of the time you're down there. So we should expect you to be in the middle on average. If we average those two utilities, we're going to be right there. And we can actually draw a line over, and if we're lucky, if I've drawn this carefully, yep, that is going to be exactly equal to the point where this vertical line from the expected consumption crosses a line connecting the utility payoffs of winning and losing, okay? And you can see that this line connecting these 2 points lies everywhere below the utility function. So this gets us to a sort of a more general argument. Suppose instead of just having with probability 50% you win, 50% probability you lose, instead let's say that, you know, the winning probability is probability p and losing is probability 1 minus p. So this is the probabilities. And what you get in each of those states, the consumption, we're going to just call C1 and C0, okay? And there's a sort of simple graphical argument you can make. So suppose we've got a line that ranges from C0 to C1. The expected utility is going to be, or the expected consumption is going to be equal to P times C1. With probability P, you get C1 times 1 minus P, or plus 1 minus P times C0. We can rewrite this, multiply that out as C0 plus P times C1 minus C0. Okay, that's just rearranging that equation. And what this is saying is that you always get at least this. That's the bad outcome. Sometimes in the good outcome you do better. And with probability P, you get basically to add the difference between these two. So we can find the expected value by basically going fraction P of the distance along this line here. Okay, so if P is 1/3, the expected value is, say, right here, but it could in general be anywhere in there. Okay, what's kind of cool then, or a kind of nice trick, I guess, is that we can take this line and we can bounce it over to the utility function. All right, so if this is C0 and this is C1, and we've got a utility function that looks sort of like that. If we want to see what the expected utility is, we can connect the utility at each of those points with a straight line and bring them over to the vertical axis like so. Let's do a little better than that. So this is the utility of C1. Here's the utility of C0. And you can see that the interval between these two is a lot smaller than the interval between here. But it's still the case that if we want to know the expected value of the consumption, this is the consumption on this axis, and this is the utility on this axis, we just go fraction P of the distance along here. Okay, so for example, if P is 2/3, we've got a high probability of winning. And we would just go also 2/3 of the way between here. And that's the expected utility. And if we've drawn it right, 1/3 of the way, these two should be related basically by this straight line. You just bounce off of it. It kind of is a way to it's like a mirror that bounces you from your consumption to your utility. And you can see that this kind of argument makes the case that whatever P is, you're going to be somewhere on this line, and then you're going to go up to here and bounce over. And it's always going to be the case that you bounce over from a point that's less than the utility you would get if you could just get that C, we'll call this C star here, for sure, okay? So if the expected value of C is C star, we're just naming it, then for people who are risk averse, the expected utility is less than the utility that they would get if they could get that thing for free. These are people who the expected utility of a gamble is always less than the utility of the average payout of the gamble. There's something inherent in the risk that they don't like. And the thing that they don't like is that when they win, because these people have diminishing marginal utility, the payoff from winning, sort of the increase in utility, is not felt as strongly as a corresponding decline in utility. Okay? So in this example, we can see that if this person could get C for sure, and then, the additional value they would feel from going from C star to C1 is not that high. But if they lost, the pain they feel is really intense, okay? And so when we weight dollars so that winning dollars don't improve our utility as much as losing dollars hurt our utility, then you get this situation where basically people are kind of afraid of risk because risk means, because the losses in a risky gamble weigh more heavily on their mind than the gains. But it doesn't actually have to be this way, okay? We could draw somebody who has a utility function that looks like this. So here's their utility, and this person's utility function looks like this. This person has increasing marginal utility. And such a person, by the same kind of argument, prefers a gamble to certainty, because for them, the increase in utility they get from wins are more strongly felt than the losses are. So I like to think of these people as guys who are sort of like, if I don't get to be a millionaire, if I don't get to live on a jet, I don't really care. Like my happiness, whether I'm lower, income, middle income, whatever, I don't really care. All I care about is getting to the top. And a gamble that has a shot at getting me to the top is way more useful to me than for sure being mediocre. Okay, so if we go through the same kind of argument, we connect up this person's utility in each state of the world. So this is the winning utility. And this is the losing utility of getting C0. And if we connect these two together, then say a gamble that pays off on average here, expected consumption being there, is less in this case than the utility this person gets from a gamble. So I don't have enough room to write that there. Let's say this is the utility of the expected consumption. And that's their expected utility. Okay? All right. So that's the big idea. I'd say the big idea is, to summarize, expected utility is equal to the probability of the utility you get in C1 plus weighted by the probability times the utility you get in C0, or in the losing state of the world, weighted by that probability. In general, if you have more than two possible cases, whoops, we translated it. All right, so where's my cursor gone? All right, so more generally, if there are n states, the expected utility is just going to be the utility in each of those n states. So probability of state 1 times the utility I get in state 1 plus the probability I'm in state 2 times the consumption, the utility of the consumption I get in state 2, all the way up to the probability I'm in, say, state n times the utility I get in that nth state. Or I could also write this using the summation notation, like so. So the probability that I'm in state I times the utility I get in that state I. And the main point is that this is not the same thing as the utility of the expected value. Okay, so here I've got the utility inside, and here I've got the utility of that whole average value. Not the same thing.